Hello everyone. I'm happy to introduce our speaker, Professor Yishai Weinstein from the Department of Geography and Environment, Bar-Ilan University. Yishai completed his PhD in geochemistry at the Hebrew University of Jerusalem. Then he did his postdoc in Scripps Institution of Oceanography, UC San Diego. Yishai was the head of geography department at Lifshitz Teachers Training College and the president of the Israel Geological Society in 2014 and 2015. The research is focused on the following directions: submarine and sublacustrine hydrology, which focus on cold seeps and submarine groundwater discharge, radium and the other uranium series radionuclides and their use for age determination and tracing fluxes between different ES reservoirs. Volcanism is focused on phreatomagnetism, the interaction of magma and surface water, and magmatic geochemistry and mantle processes. Please.
Supposed to talk in English, right?
Sorry?
Okay. Okay, hi everybody. Okay, so I've put a photo of Dobe. I guess that most of you know this place. That was, I would say, the background for some of the things that I will show today. But what I'm going to talk about is not only about this groundwater coming out of of what we call the subterranean estuary, but in general about some of the applications of radium and some other radionuclides to ocean and earth science. So these are names involved. These are some of these people involved in the researches that I will talk about. And just to remind or to show the main actors in these things, we are going to talk mainly about radium, not only. And as most of you know, maybe not all of you, radium isotopes, there are 4 naturally occurring radium isotopes. All belong to what we call the uranium-thorium series. To those who are not familiar with, these are chains of decays, like waterfalls, one decay to the other via radioactive disintegration. In this case, that's the chain of uranium-235, even though actually it is produced by plutonium, but you see it's a short-lived one, so actually that's the head of the family. This is the thorium-232, and then there is the common uranium-238. And radium is somewhere in the middle. Here is the first one identified by the Curie couple down there. And then this is the longest lived radium. The numbers you see is what is called half-life. I guess all of you, most of you know, so I don't have to explain. But it gives you an idea about the times involved with this isotope. The other ones, 2 of them belong to the thorium-232, the radium-228. Some, let's say, medium-lived, a few years. It's useful up to 20, 30, maybe 40 years. And then radium-224, which is the shortest, only 3.66 days, namely after 2-3 weeks in a system without reproducing by its parent, the thorium, it's actually disappearing. And then there is another one in the other chain, which has a half-life again of a few days or 11 days. All radium isotopes are being produced by thorium. And that's part of the game of the radium, why it's such a useful radioisotope for systems that involve water-rock interaction, because thorium is highly particle reactive element. So its isotopes, whatever they are, the common thorium, the 232, will be in the rock, of course, but also the others that are produced on the way through the chain decays, they will always be on particles. So if they are produced in the water, they will find the first particle and absorb to. And the radium are being produced from the surface of these particles and being released to the water. Some of it reabsorb on the material, some of it remains in the fluid, in the water. So we can get a lot of information in systems of groundwater and systems of water circulating through the aquifer, etc., etc. Even in the deep ocean, we can get an idea whether about water, when was the last time it saw the coast, or about mixing of surface water with deep water. Deep water are in contact with the sediments at the bottom of the ocean, etc. And not all, but 3 of the isotopes are decaying to radon species. The radon-222 is the most famous one. It's the longest lived. The other ones, the other ones are very short lived. This is what was used to be called thorium, etc. So there are, except for the 228, which does not produce a radon on decay. So these are the actors, and here you have a summary of the things. 4 naturally occurring isotopes, all are radioactive. Radioactive means they decay, but they are also being produced by decay. Covering wide spectrum of half-lives, you see the numbers. Enriched by interaction with aquifer solids, as we said, because the thorium is there. Very low in the sea, because in the sea there is not a lot of thorium, so they are not supported. That's the word. They are not supported. Nothing producing them, only in contact with solids, aquifer, sea, bottom sediments. Salinity is a major factor in radium mobility. That's why saline water will get more radium in solution, fresh water, less. Redox state is another major factor. Actually in anoxic environment, radium is more mobile. In saline environment, radium is more mobile, and we'll talk about it a bit later. Okay. And one of the first works that was done, of course, Broker is involved. They did the work and compare the profile, in this case, of radium 226, the long-lived, the famous one. They compared the profile in the Pacific and the Atlantic, and they found that actually in the Pacific, as you see, activities, let's say like this, in surface water, they are low, and they are similar in both oceans, Atlantic and Pacific. While when they went down, they saw that there was an enrichment down to the sediments, which means radium is coming by contact with the sediments, as we could expect in the middle of the ocean, but in the Pacific, it's higher. So the conclusion was, of course, if the Pacific is higher, it means longer contact. So the conclusion was, in the Pacific or Pacific bottom water, spend more time, they are older, they spend more time next to the sea bottom. Afterwards, they got to the conclusion that this was a mistake, but never mind, I'm just giving it's about the residence times. Even they got a number, a deep Pacific 3 times larger residence time or ventilation rate than in the deep Atlantic. In any case, we went with the radium first close to shore, and we worked all over the coast from Rosh Hanikra down to even Gaza, but down to Ashkelon in terms of Israel. And we chose Dor as a natural lab. It's very convenient. First, you have the hotel next to the water. Second, it's a enclosed embayment. So if there is a signal coming from the sediments, from the aquifer to the water, mixing, is less. There is higher residence time in the coastal water. You can identify whatever the signal is easier. So I would talk, in any case, I would try to talk. I'm sure I won't finish. I didn't have time to take slides off, so slides out of the presentation. So we'll see. I'm going to talk about land-sea subterranean conveyor, which is called submarine groundwater discharge, another way, which is the road groundwater take on the way to the sea, direct seepage of groundwater. Then I'll talk a bit about groundwater age, or water age in general, and then I'll try to talk about what we are doing these days, which is work in the permafrost in Svalbard in the Arctic Ocean, also using radium isotopes. So, as I said, applications, not necessarily only SGD. So the first about this SGD, submarine groundwater discharge, a direct discharge of groundwater to the sea. That's an example in Dore Bay, in Dado Beach, those who spend some time next to where the beer festival is taking place sometimes, and do not drink too much beer or do not play the ping pong, look at the water sometimes during the low tide. You can see things like this. This is fresh water coming out. I guess, I mean, I never worked specifically in Dado, actually I did, but we never did of it a big deal, so I guess it's directly from the Cretaceous in this case, not from just from the sediments. But this is an example. This is another example of a plume of fresh water coming, in this case in Florida, where there is a lot of fresh water coming out directly to the sea. Here is in Shikmona in low tide. I don't know how is it now. There was a period when Rambam was doing all the works. They took the heads of the groundwater very low, so it stopped. But until 10 years ago, during low tide, there was streams of fresh water coming directly from the Cretaceous rocks to the sea between Shikmona and the Hofa Carmel, and that's Barak sampling some water from nutrients. This is the legend about the Phoenicians pumping water from the sea. They were used, according to the legend, they would take a funnel, put it upside down, let the fresh water come up and fuel their boats with fresh water. The legends goes on and say that that's the way the Phoenicians in Tyre and Chor survived Alexander the Great at the beginning, because they had all this water coming out from submarine springs. Lot of stories about, actually stories about SGD in the world are mainly from the Mediterranean. Lot of stories, lot of places in Greece, in Italy, Adriatic, Gulf of Lion, Mallorca, Minorca, Spain, all over, especially in the north where there is karst. So there is huge plumes of fresh water, but SGD is not only fresh water. Here you can see. It's in Hebrew. So I'll just say we also have in our sources from 1700 years ago stories about the well of Miriam, which is mentioned in the Torah, but actually it is SGD. What is the well? SGD. So that's all kind. Stories about SGD. I can tell you that in the memoirs of Judith Montefiore, the wife of Moshe Montefiore, I remember it before I started working on SGD, she said how they arrived at Tiberias on top, like where now Shikun Gimel is. They looked down to the Sea of Galilee. They saw the well of Miriam, the sister of Moshe, in the middle of and they paid a few shillings to the local fishermen to go and bring them a few liters directly from the well in the middle of the Sea of Galilee. So it is. In any case, that's SGD. The idea is that water is coming out directly to the sea from the aquifer. It can be a phreatic aquifer. It can be a confined aquifer. I assume people know the terms. If not, excuse me. In any case, what is important is there is fresh groundwater coming from the aquifer due to hydraulic gradient between the land and sea, like in usual hydrology. And there is circulation of seawater, which is not the same. And circulation could be in long scale, namely it goes into the aquifer, then goes out along the mixing zone, which is the fresh saline water interface here and in the confined aquifer. And it can be very short-lived, like hours, etc., due to waves, due to coastal currents, due to tidal pumping, low, high tide, etc. So there is fresh SGD and there is saline SGD. And, okay. And then some 20 years ago, there was the first big publication about it. It was of the person that became the prophet of SGD. His name is Billy Moore from, now he's retired from South Carolina, from the University of South Carolina. And he had a paper in Nature where he used radium to show that radium 226, the long-lived, is getting lower in seawater as you do a profile, in this case of 100 kilometers. Okay, it's not our shelf, it's the shelf of the Carolinas. So that's about, you can see 100 kilometers, even more, 120 if I remember well the number. And it's going lower and lower from the shallow shelf to the outer shelf. And he made calculations about how much water he measured the radium in coastal water, and then he calculated how much water with this amount of radium should go there in a year, in a day, never mind, in order to supply or to create this profile, this gradient. To those who don't see, this is 20 something. The units are usually dpm per liter. In this case, I guess it's dpm per 100 liter. I don't see the units, but that's usually how we do it in the sea. It's dpm is disintegration per minute. How many pumps, how many pulses there are of an atom that disintegrates, in this case, to radium. So that's how we measure it. We don't measure it by milligram per liter or by ppm or ppb. We measure it by activities. How much? Per volume of water. So he calculated how much, and the conclusion, I think I highlighted it, the conclusion was, I concluded groundwater flux to these coastal waters must be about 40% of the river water flux during, etc., etc. Namely, it's the order of river flux to the ocean, the SGD. And then when all SGD started getting more and more attention from the scientific community, and people did work, and we did also work in Dor. And this is the geology of Dor, the Kurkar, the regional aquifer, clay in the what we call the Marzeva, the trough, and then some local sands, and this is the Kurkar. Okay, now we know that the stratigraphy is, there is 2 units of Kurkar, 2 units of confined aquifer is here, but never mind it. Both the Kurkar, which is the calcareous sandstone, and the sands are exposed in the bay where we work. This is the bay, so this is the Kurkar, exposed like 60% of the surface of this bay is covered by the Kurkar, by this hard rock, calcareous sandstone, and the other 40%, 50% is by loose sand, this unit. And what we showed was, we found these are numbers. This is the salinity in piezometers that we located here. Now we have here a lot of other piezometers to the different units, but these were in the phreatic aquifer, and you see the numbers. You know, this is the salinity of seawater, PSU, and this is in the shore. But when we went and put seepage meters that let the water flush through, and then we measure the salinity, what we got, these are seepage meters. We use now smaller, but never mind. The numbers we got this was mixture of fresh water and saline water coming out of the sediment. Okay, mixed SGD, circulated seawater, circulated I hope everybody understands in Hebrew, mesuchorim, okay? And fresh groundwater, which gives us everything. Now we even got water down to 3, which means sometimes there is hot, cold spots of fresh water coming out. Usually it's mixed. And what we showed in this case by radon, the daughter of the radium, the thing that is produced from radium, we showed that seawater have hardly any radon in it. This is again dpm per liter, disintegration or decays per minute in a liter of water, of radon 222. So you see here are hundreds, that's the scale. Seawater have hardly anything. Fresh water, ignore these ones. Fresh water has a lot, hundreds of, and you see this is what we collected. We stood in the sea with a small boat like of kids, and we pumped tens up to 100 liters of water, and we saw how much radon there is, and you see that it's somewhere on a mixing line, some outliers, but in general it's on a mixing line between seawater and fresh water. Again, this is salinity. So there is here a mixture of circulated seawater that goes into the sediment with fresh water, but we see everything is on a mixing line, namely the conclusions are that radon is, first of all, it's a tracer, but it is enriched. Okay, all of this, where is the conclusions? 1 second. I forgot all of this, okay. And these are the conclusions. The radon arrives at the bay only with the fresh groundwater. There is no radon leached from the sediment, even though there is radium there, with the seawater that circulates. If it was like this, we would get samples like this here with radon in, because it sees radium, it collects radon, it comes out again. Since radon has half-life of a few days, it means that if the seawater circulating was spending there a few days and more, a week, we would get relatively high samples like this with high radon, but we didn't. Namely, the circulation is short. It is circulation, but it's short. Due to waves, due to whatever it is short scale. Yeah? The time range is short. And seawater circulation is radon poor, namely it is short. There are some other conclusions about to what depths it arrives, but let's skip this. Yeah, I wrote shallow, but let's keep the short-term circulation. And that's just a drawing that tries to say the fresh water comes from here, the seawater is doing a shallow, never mind whether shallow, but short circulation in the sand, and mixes with the water that comes from below, from the kurka, goes out to the bay with mixed salinity, but the radon is only the fresh water, the regional aquifer water coming out after spending in the aquifer enough time. And for radon, you don't have to spend thousands of years. It's enough that you spend there weeks, a few weeks, and that's it. Actually, a week is enough in order to get the maximum radon, 2 weeks. Okay, so we went, since we don't, and I want to show you different applications, I'll do it in general. In order to get an idea, we wanted to see, okay, how much water is coming out of the sea. So we were lucky because we identified in the previous photo that actually the radon is a proxy, like gives us an idea about the freshwater discharge to the bay. The fresh water, not the total SGD. It doesn't, because even if I will increase the seawater circulation, it won't change the amount of radon coming out of it. It is the fresh water only, which is not always the case. In this case, so the radon can give me an idea by mass balance of how much fresh water is coming out to this bay. So we did a mass balance by doing time series and looking at the changes in the flux of the radon to the bay. What did I want to say? I don't remember. Never mind. So we measured radon. First of all, you can see very easily, this is the radon, the red. And this is the sea level, okay? Measured both in the bay and in Hadera, the the IOLR station. And you can see that there is negative correlation, namely, when there is high tide, radon is low. When there is low tide, radon is high. That's tidal pumping. Fresh water, it's not about the seawater, coming out strongly when the tide is low and being actually pumped backwards, like reverse pumping, or at least doesn't come out when there is high tide. We translated it, I won't get in details, we translated it into radon inventory. You take the volume during high tide, during low tide, etc., of the water in the bay, and you multiply it by the concentration, what I call the activity, how much radon there is. Then we had to correct for a lot of things. We had to correct for radon evasion to the atmosphere, which is one thing, for the mixing with the sea during high tide, during low tide, all kinds of considerations. There is a whole protocol. You can believe me, you cannot believe me. But bottom line, we arrived at the end. This is again these two, radon and sea level, and this is the advection of water. At the end, we took what we got at the seepage meter, how much radon is coming out with fresh water to the sea, and we divided the amount of radon coming out, the flux of radon, by how much radon there is in a liter. And then you can get how much water is coming. So first you can see sometimes there is hardly any water coming out to the bay, sometimes there is a lot. Bottom line, we got a mean, in this case, which was May 2006. We got a mean value of 5 centimeters per day. Soon you'll see 5 centimeters per day is not so little. It means that all over the bay, on average, there is 5 centimeters per day of water, of fresh water only, coming out. We did a multi, we measured it for 2 years, like 5 times, so we got a little bit low, so we took 3.5 centimeters per day. So what is the SGD action at the bay? Let's finish with this. So this is 3.5 centimeter, it's by meters per day, and bay width, let's say 100 meters. Nobody said that there is no fresh water coming out beyond the bay, but we took only the bay, 100 meters. Length, 1 kilometer, it's 8. But I took 100 kilometers, which includes, the 3 bays, never mind. I wanted to know how much is coming out per year along 1 kilometer of Doe Bay, assuming it's the same. And you see more than 1 million cubic meter per year. That's only the fresh water. And this is a lot. Because it means if this is the case also, okay, maybe it goes by hotspots, but I'm sure that in Shikmona there is more coming out than in Doe, and in Jisar Azarka, and in Atlit, and in all of this. Once there is Yagur, one there is the coastal aquifer, one there is the Cretaceous. Let's say this is a typical number, it means like 40 million cubic meter, okay, let's say 20. But 20 million cubic meter, 22 now, is what is pumped all over the Carmel now for local use, just to give you the scale. So it's a lot. I don't mean it's bad, I just mean it's a lot. When I went to hydrological service, they said, okay, it's okay. Okay, now let's move from this to the global scale. I want to show you how because in the last few years, since 2008 until 2015, there were 3 papers, including one of us, that looked at the regional to global scale of SGD using radio. But first I want to show you what is in the books about fresh groundwater, because radium, as I told you, is going out mainly with saline water. Clearly it's not about fresh SGD. So first about fresh SGD, due only to hydrological considerations. There was a book published by some 2 Russian scientists, Zektser, and I forgot the other name, and they made global thing. So these are the numbers about the Mediterranean, for instance. Subsurface runoff to the Mediterranean Sea, Zektser and Zamalov. And you see the numbers. Total in cubic kilometer. Cubic kilometer is 1 billion cubic meter, okay? So it's like 70 cubic kilometer cubic kilometer, only to give you the scale, total Med River flow, 310. So it's like 1/4, it's not so low, talking only about fresh water. That's the Mediterranean. And, okay, and if you calculate per kilometer, it comes very close to what we found in Dor, which means Dor is in the middle, because clearly in North Africa there is less water coming out than in, let's say, the Adriatic or Gulf of Lion. Okay. Global, the same book, but some other, I took some other estimates, so that's the number. Hundreds to thousands of cubic kilometers, while global river flow is a very nice number that everybody can remember, 40,000. So talking about global, it's the number is a little, the proportion is a little bit lower. It's like 10% or 8% is the number I usually use. But still, it's not negligible, okay? Then this is, Hebrew, fresh water. What about the saline water? So we can use radium, okay, I'll skip this one because this is not global, as you see, it's somewhere next to Los Angeles. But here, the first paper came out 2008 in the first issue of Nature Geoscience by the same Billy Moore. Billy Moore wrote a paper. He had a lot of radium-228 measurements along the years. He made a mass balance. Why radium-228? Because its half-life is close to 6 years. Namely, it's usable for years to tens of years, which is good for surface water. So he made mass balance of the surface water of the Atlantic, and he made radium inventory, of course, what is decaying, what is scavenged by particles going down, what is coming by rivers. The blue is for sources, the red is for sinks, what is coming in with dust, of course. And then what is left is the SGD, and he arrived at the number. What is important is not the number because you won't remember, but he arrived at the conclusion that in the Atlantic, the amount of water, again, he took then endless amount of wells and springs, coastal wells, etc. And he made statistics on their radium content, and then he took the radium balance, divided it by how much radium there is in 1 liter or 1 cubic meter of water, and got how much water has to come in the order of rivers, and this includes the Amazon. Okay, now I remind you, that's mainly saline water. Now you say saline water, who cares, it circulates. Yeah, because the story is not only water balance, it's about what's coming out to the oceans. When you do ocean balance, today there is the Geotraces program and all of this. When you do ocean balance of uranium, for instance, clearly SGD is a major factor there. If you do strontium isotopes in the ocean, which is a story that it goes through decades about the how strontium isotopes changed in the global ocean, SGD is a major factor there. So it's not only about water running out to the sea, or we lose water. That's not the big issue. The big issue is the effect, the impact on the chemistry of the ocean. So, so numbers, and then came our paper in the Mediterranean. We did the same, a bit more in detail, but the truth, less samples. We did one cruise from Istanbul to Vigo, and a little bit complementary. And then we did all of this atmospheric dust, Bosphorus, Gibraltar, exchange with sediments, mixing between surface and deep water, profiles, etc. We did, never mind the details, but again, we had more output, more sources than sinks, namely something has, again, of the same isotope here, radium-228. There was more 228 lost to the system than coming in. So the difference should be coming by unknown sources, which is SGD, submarine groundwater, this mainly saline. So the numbers are again, we did all of this. We got that it should be, that's the numbers by, you see, 10 to 15 disintegration per minute per year. Never mind about the units. But But that's the imbalance of the radium. And then we did all the things around, including data from DOE, including data from all over the Mediterranean. And there wasn't data from the Nile, but there was from Morocco, and there was from Tunisia, and there were everywhere. And we took, you see, we did some statistics, and bottom line, the total SGD is these numbers, and you can see the river and floods. Now, the Mediterranean, as you know, is not so rich with rivers. So in the Mediterranean, you see, even if I take the lower number, it's like the river, but it could be 1 order of magnitude higher. Again, it's the circulating seawater, but that's important. That's important because if you do something about the chemistry of the sea and you're trying to see sources, sinks, you have to take it into account. Okay. Okay, I did here all kinds of tables, but the idea you got, you can see total SGD, fresh SGD, etc. It's not the same in all places. You see that, for instance, if I talk about total SGD, you see that the Atlantic is a lot higher, the Med Sea is a lot lower. We can talk about it, why, etc. I mean per kilometer, but we'll skip it now because I want to talk about, it's late. I'll skip also the nitrates, which is of course a big issue in SGD. And I'll go directly to water ages because I want to show you. Sorry. No? Don't learn from it. Yeah. So I want to talk about water age because that's our main, doing water age, especially, I'll show also about the sea, but doing water age in the aquifer is a big issue. You may say, there is no problem, we have carbon-14. Carbon-14 is not so straightforward. There is what is called dead carbon, and there are some people here maybe that know more than I do. It's not always goes the way you wanted it to go, so it's always better to develop other methods to define determine the age of water. The advantage of, for instance, carbon-14 is if there is no carbon coming from the rocks, it's very convenient. We do the age of the water by determining by a signal that is coming from outside the aquifer. And it's just decaying when it's in the aquifer. With the radium, it's always a lot worse because radium is being produced through the aquifer, so the considerations are a lot more complicated. But if you manage to do it like we did in the Dead Sea, you're okay. Now we are trying to do it in the coastal aquifer and we are in trouble. So I'll show you what we did here. As you may know, in the Dead Sea, the fresh saline water interface is very shallow due to the huge difference in salinity between the Dead Sea water and the fresh water. And so it's very, very shallow. Actually, close to the sea, there is no fresh water at the surface. There is only the mixing zone. So here you see all the red is circulating Dead Sea water up to 100 meters and more from the sea. That's the sea. While here, that's the mixing zone. Yeah, that's the surface, and that's actually the water table. Okay, so we had a lot of pumps. It's the area of the Arugot Delta and alluvial fan, and we had a lot of boreholes, and we sampled water and measured the radium there. But even before, there was, in the same paper, we put another method that was done by Yael Kiro, who did her PhD here. She was measuring simply, it's a very simple thing, and I think some of you know that the sodium chloride ratio in the Dead Sea is getting lower with time, since at least the 50s or the 60s, I would say, yeah, of the 20th century. Because it was used to be, the ratio was used to be like this, 0.30 something, and now it's 0.21, maybe now it's already even 0.20, due to the precipitation of halite that takes it down. Now, she measured in these boreholes, she measured the sodium chloride ratio, and she saw that when you get into the aquifer, you get higher and higher number. Still in Dead Sea water, the salinity is exactly Dead Sea, only the ratio is different. And then she could, since we have documentation of what was in the Dead Sea since earlier than the 50s, we know very well that when you get a ratio, now it's 0.21, or it was, and here it's 0.27, that's ratios of the 70s. 0.25 is ratios of the 90s. 0.23 is like a few years back, etc. And here is actually when she made the measurement, which means until here it's like one system, and here it goes all the. So she got here an idea about the age. Water here was like, back then when she did the work, were like 30 years old, here they were 20 years old, etc. And she could get the rate of circulation of the Dead Sea water doing something like this, which you can do by yourself, 100 meters or 90 meters to 80 meters per 30 years, so you can get the rate. But she did it also with radium-228. What she did here, she measured the activities of radium-228. Again, it has a half-life of about 6 years, with distance from shore inland in the saline water of the beneath the interface, not the mixed water. Dead Sea water in the aquifer. What is the radium-228? You see next to the lake, okay, in this drawing the lake is to the left. You see next to the lake, the radium-228 it's not 0, it's like 1, because in the lake it's something between 1 and 2. But then it's being built up. Why it's built up? Because it's in contact with the sediments. Sediments have thorium, so it's being built up and until it gets to a plateau where it cannot build up again. And you can see that there are actually here 2 lines. Most of the data fits this data, one or more than one fits this line. And by modeling this build up of the radium with distance from the sea, you can actually know the rate of the seawater advance into the aquifer. So this one is like, here it's like 1 meter, let's say the closer the plateau being reached to the sea, the slower the rate. So for instance, this one is like 1 meter per year of water getting in, while this one is like 10 meters per year, it's this one. Yeah. So you can see that it's between 1 and 10 meters per year. You get an idea about the flow rate of the seawater, of the Dead Sea water, into the aquifer, which is more or less in agreement with the sodium chloride. If it was there like 30 years, 90 meters, so it's like 3 meters per year. So it's in the middle, like 1 to 10. Yeah? So we are talking about meters per year of rate using radium-228. We are now doing a project, okay, I would show, in the coastal aquifer, mainly in Nitzanim, but also in other places, trying to use 226 because we are talking about hundreds of meters and slower movement of the water. There, the aquifer is alluvium, it's moving a lot faster. So, and we cannot do it. Why? Probably because the sediments, they are not yet in equilibrium, in what is called in isotope geochemistry, a secular equilibrium. The parents of the radium did not attain yet the concentration they should have because of all the changes that the coastal aquifer went through. In order to attain it, you need hundreds of thousands of years, which probably the aquifer didn't yet have. So we don't get good numbers. We get good numbers when we go into deep boreholes in the coast where there is saline water, but into the Cretaceous. There we get good numbers, and in another seminar I can show it. So maybe it's only applicable to this. Okay, I'll go through this. Sorry. I know it's not the right way to do it. Maybe I'll show this one. Here you see radium-223 versus radium-226. This is a secular equilibrium line. What is the meaning of secular equilibrium line? This is the line that is dictated by the parents, the radioactive parents of the two chains. Radium-223 is produced from uranium-235, while radium-226 is produced from uranium-238, the common uranium. Now their activity ratio, activity, not concentration, is 130 something. Activity ratios is 21 point something. And this is the line that says that these two isotopes are in equilibrium. In order for these two isotopes to get in equilibrium, this one has to get to equilibrium because it's a lot longer lived. This one has a half-life of days, this one has of 1600 years. So it takes several thousand years, like 5 half-lives, 8,000 years in order to get in equilibrium. And what you can see here, without getting into all the groups, these are water from all around the Dead Sea. You can see here, that's from one of the papers of Yael, you can see that the green and the brown groups are very close to this line. The green are the eastern catchment of the Dead Sea, namely water from Jordan, getting to the sea, interesting. And the brown is Ein Feshcha, that's interesting. Both Ein Feshcha water and Feshcha is not Sukkim, you know, northern part of the Dead Sea. Both Ein Feshcha and the eastern catchment water document very old water. Now the question is, does it mean that every drop coming out in Ein Feshcha is, as I said, several thousand years old? What is the meaning of several thousand? It means that it didn't see the atmosphere for several thousand, it was in the aquifer. That, or that the signal is brought by water that did it, but not all the water. Namely, it's a mixture, but the other water does not have a radium signal. So after you define an age, you have to start thinking the real meaning of it. But no doubt that there are two groups here that bring a very old signal. The others are yes and no. For instance, Ein Kedem, you would expect it to be on the line. You know, Ein Kedem is the main thermal springs on the Dead Sea shore. Some yes, some no. So the question is again, so what does it mean? That there are new water? No. So what does it mean? Good question. But whoever wants to see, there was a paper of Yael, it was in GCA. You can see from 2015. There she discussed all of it, but if you ask me, the questions are still open about what is the real story of each group of water, but that's interesting. Also the difference between the eastern and the western catchment. And okay, this we already saw. I will jump to the end because it's the, I would say, the more, let's say the more recent thing. Okay, I put Yishai Weinstein because he said what is written here, that imagination will take you everywhere. I mean, sometimes you are bored with this country, so Itzik is going to look for Eratosthenes and others are going. So I was thinking about how can you get the furthest away from here. So, okay, I got a Eureka, which was Svalbard. Svalbard is this island or archipelago, how do you say it? I don't know, in the Arctic Ocean, 78 degrees north. The northest place, you know, what's his name? John Hall is working there for a lot of years. And the idea was to work on permafrost. Why? Because everybody knows that sea ice in the Arctic is shrinking. Even those that say that human being has nothing to do with what's happening, nobody argues that sea ice is shrinking. Ask the Russians. They are gaining a lot of profit from their boats making the way through the Arctic Ocean instead of going all around the place. And they build everywhere. There soon we'll have a war there about the oil, see how the Norwegian reacts, never mind. But yeah, that's the shrinking of the sea ice, but on top of the sea ice, there is also the permafrost. The permafrost is this frozen soil, like forever frozen soil. Usually it's frozen since, yeah. Where we work, it's like thousands of years. And the idea is that when sea ice shrinks and allow more transportation, permafrost also shrinks, and actually the transportation is being, it's not good for transportation because There is less months you can, for instance, travel with trucks along the frozen surface in the Alaska, etc. But never mind if it's bad or good, the idea was to try and find isotopic signal for this shrinking of permafrost. This is the map of permafrost. The green is the continuous. Svalbard is here. Okay, we work here in this spot. It's called Longyearbyen. That's the only town there. And okay, and the idea was that that the permafrost or the amount, or the surface that is covered, now it's like 20% of the global soils. But you see, there is, if it's now, or it was used to be in the 80s, it was used to be more than 15 million square kilometers. You see different, first of all, you see that it shrank. Some places that were continuous are now patches of permafrost. Second, it will go down significantly, like almost some say by half or more, toward the end of this century. So we wanted to, and that's what happens when the permafrost, that's why all the houses are building on pillars, all the water tubes are on top. You go and the water tubes are along the roads because you cannot do it in the permafrost, not to talk about the gas. So the idea is to find a signal. That's the permafrost. Yeah, I guess whatever I do, it will be the last minute. This is the permafrost, and always there is an active layer on top which freezes in the winter and then defrosts during the summer till September. Okay, there are no trees there, it's tundra. I don't know why there is trees in this. That's how permafrost looks, active layer. And usually the way to see that something changes is simply to measure by drilling spots and to see what is the thickness of the permafrost. Or permanent boreholes where you measure the temperature, and if you see that the temperature goes down, you are sure that something is being thawed due to the warming there. So we decided to go there and try to identify a signal of permafrost water. So then maybe we can see it in the water above. If I go to a pristine place and I can look at the active layer where there is water during the summer and see the signal of a permafrost, I can say, oh, this was permafrost, now it's not permafrost anymore, it's freezing and thawing annually. So this was one. Second, to try and identify the freezing age. And I'll go through the next slides. Okay. The idea was that since it's a frozen medium, the area, so things that happen usually with groundwater won't work here. For instance, radium that is being produced by decay usually goes out with the groundwater. Here it's frozen. So the longer it's frozen, the more radium will accumulate there. Now, working with the short-lived won't help me. It's days, weeks, months. So we took the radium-226, the one that is now, which means this system is working only for thousands of years. So the idea is that here you can see a radium-226 will be thrown, ejected into the pore space, but will be stuck there. So it will grow. So this was the idea of the signal. There was also an idea to do it with lead-210, what Vital is doing here, but never mind, it doesn't work. That's the area where we were working, a big glacier valley called Adventdalen, and that's the way you do it. That's in the summer. Yeah, you drill in, you get, first of all you dig, you can see, you dig a ditch, you get to the top of the permafrost, it's like a cement, and you start drilling from there. You see, there I felt that I'm not so heavy like I was used to think so, because it didn't work too much. And you see, that's how the cores come out. You have to go out with a rifle. There is more polar bears than a human being. Here you see a bottom, that's the top of the permafrost here. And here you see, just we came back a week ago. It's already spring, but you see how you work there. Everything is frozen, including the active layer, so you can get the active layer as it is a permafrost. But of course there is difference. We were cutting it, we crushed it, etc. I'll just get to some of the data. I don't have yet the new data, only the one from the two last summers, what we see here, and by this I'll finish, what we see here, and it's a very Sisyphic work. Each sample, only to process, take like 2 days. So, at the end we have some data. And what we see here, take it up, like rotate it half a circle, 90 degrees. This is like representing the active layer. Usually there it's between half a meter and meter. And this is top of permafrost down. And what you see here is radium-226, what I said. But since we didn't know what happening during, you are taking ice, poor ice, you're doing all kinds, I don't have time to tell, but all kinds of, we failed, we didn't get, and you thaw it. The minute you thaw it, some of the radium can get lost. So what you actually do is say, I will normalize it, like we do in instead of using concentrations, I will use ratios. I will normalize to what? To something I know that always gets there to the maximum, which is the short-lived radium. So I divide it by the radium-224, which is the shortest lived. So never mind if I lost radium, I lost both of them. So it's normalized and I can use it. And what you see is, first of all, you see that really the active layer is a lot. These are water taken from the active layer. The radium-226, or its ratio 2, is a lot lower than in the permafrost. Namely, there is a signal of the permafrost, what we wanted to actually do, which is already an achievement. Second, what nobody, I'm going in 3 weeks to a permafrost meeting once in 3 years, and they will all kill me. Because they assume this is sedimentation, it's being, the ages are by OSL, and we know it's like accumulating Aeolian sediments, like the less in the Negev, only here it's periglacial. And they all assume that the freezing goes with accumulation of the sediments. It's all Holocene. So there is a layer, water gets in, freezing after a while, another layer. So the freezing should follow up on the sedimentation of the sediments. But here, this means higher 226 next to the top permafrost. Lower, okay, I don't know what to say about this. I'm waiting for what we did now, in May. But in general, we see 4 different places. All of them show different things, but all of them show somewhat. I'm not talking about the depths. The permafrost is tens of meters, there are somewhere hundreds of meters. Talking about the first, it's in centimeters. So I'm talking about 1 to 1.5 meters from the top of the permafrost. So it's like inverse or reverse. So the question is, what does it mean? There was a period that nothing frozen and then it started freezing from the top down, which makes sense. Question if it works, if modeling, one modeler told me it doesn't work. It should, even if it comes from above, it should work. Okay, let's see. But that's one of the things, because there is no other way to determine age of freezing. Everybody determines the age of sedimentation, not of freezing of the soil. This summer we are going to check about Siberia. There everything is a lot older, so we have to use other methods, more longer lived from the uranium-thorium system, but it's not so simple. So okay, so that's the what we have, preliminary results. What I said is written there, and I think we are just at the beginning, and these are they looked white now, but in the summer they become brown, these reindeers, and everybody eats them. They stopped eating the whales, I don't know why.
Okay,
That's
thank you
it.
very much.